Push that rock with some sick 'em bears. So we want to integrate this product that also has a composition function here, but we don't have a quote-unquote chain rule or product rule for anti-differentiation. In fact, up until now, all we've integrated are polynomials and then functions that we happen to know the antiderivative for. And this is not one we know offhand, so how are we going to handle this? Well, there's techniques that we're going to learn, most of them next semester, but one that we're going to learn this semester is called U substitution. So we're going to use U sub, it's frequently called U sub, because we're going to let U be equal to a part of the function that we feel like is an antiderivative of the other part of the function. So we're going to look inside here and see if we see an antiderivative. Well, e to the x is always its own derivative and its own antiderivative, so we'll let u be this e to the x here. And then we'll get the derivative of u with respect to x. Well, give birth to the mother, you get e to the x. And then what I'm going to do is I'm going to use that trick we learned when we were studying linearization and differentials, and we're going to get the differential of u. And the way we're going to do that is multiply, weirdly, by part of the symbol, because remember Leibniz used this notation because he realized at times you could treat these as two different quantities. If you change the x just a little, then there's a little change in y. So we multiply both sides by dx and we get the differential of u. Now, what that's going to do is up here, I'm going to rearrange this a little just to help us see what we're doing here. So we have cosine of e to the x being multiplied by e to the x dx with respect to x. So normally we read this integration of this integrand with respect to x, but I'm going to look at this and replace it. See, it's right here. I'm going to replace it with du. So du is going to go right there in that place. And then I'm going to have this. But remember, we let u be e to the x, so I can put a u in there for e to the x, and we're integrating. And the integration of cos is sine. So we get sine of u. But we don't want u because our variable was x. So, oh yeah, u is interchangeable with e to the x, so I can rewrite it as sine of e to the x. And don't forget your plus c, baby. And that's how you do that. IGGY. Now, is this correct? Well, if you're not sure, check. Take the derivative of your answer, of your antiderivative, and you should get back to the integrand. So now this is a composition. Sine is being composed of e to the x, so we get the derivative of f, which is cos. And then we evaluate that derivative, at g. So when I evaluate cos at g, I get e to the x in there, in place of that x. Now, meanwhile, the derivative of g is e to the x. And then the way you get the derivative of this is you multiply f prime of g by g prime. So I take this cos of e to the x and multiply by e to the x, and yes, that was our integrand. See, e to the x times cos of e to the x right there. So check, that works. And that's how you check your work. Just take the derivative, see if you get your antiderivative. So here's another example. I'm going to let u be this denominator. Why? Well, because I know that x to the 5 is an antiderivative of x to the 4. So it makes sense. I get the derivative of u with respect to x, which gives me 5x to the 4, and then the 3 goes to 0. I don't have a 5x to the 4, so that's a little tricky. But we'll go ahead and get the differential of u, because we want a differential of u, so that means I multiply by dx. And then I say, well, I would like this to be a 2, not a 5, right? See how I have a x to the 4 dx and an x to the 4 dx, but this 5 and 2 don't match up, but that's okay. Now, you can't, students sometimes do strange things here. You can multiply both sides by a number. But starting to multiply by 1 over x or something like that, that's nonsense, okay? You can't multiply by variable expressions that might be 0. But I can multiply both sides of the equation by something like 2/5. You can multiply equations by constants. And now what does that give me? Well, it gives me 2/5 du is equal to 2x to the 4 dx. So my numerator, notice my numerator is 2x to the 4 dx, and that's exactly what 2/5 du is. So I'm going to put 2/5 du in my numerator. And what's my denominator? Well, my denominator is u is equal to x to the 5 plus 3. So I have a u here. Now I'm going to kick the 2/5 out. It's a constant, so we can kick it out and just have 1 over u du. Oh, this is the reappearing log rule. We get the natural log of the absolute value of u, and it's being multiplied by 2/5. But we don't want u talk, we want x talk, but u is interchangeable with x to the 5 plus 3. So x to the 5 plus 3, and it's being cut in or multiplied by 2/5, and don't forget your plus c bay b, and there's your antiderivatives of this. I said plural because c represents an infinite number of constants that you could add in. One last example that we should talk about. By the way, this function e to the negative x squared all by itself, if we were trying to integrate it, you can't. So if you give me any nice function, not a psychotic, remember those neurotic functions we studied at the beginning of the semester? If you give me a nice function, I can take the derivative of it. But if you give me a nice function, I might not necessarily be able to take the antiderivative of it. So sometimes these are challenging problems. But with this x here, this is not bad. This is a lot like our first example. I'm going to let u be this exponent up here. I mean our second example. Anyway. So I'll let u be this. Why? Because, see, this polynomial is one higher than this polynomial. This is a quadratic, so it's going to be an antiderivative of a line. Now, it's not that line. It's because du dx is negative 2x, and I have just an x here. But, you know, that's easy to take care of. If I want a negative 2 here, how about if I multiply by a negative 1/2? That'll give me a negative 2x e to the negative x squared dx, because a negative half times a negative 2 gets me back to this. So I haven't changed my integrand any when I multiply by 1. Now I'm going to multiply both sides of this by dx so that I have the differential of u. We want the differential of u, which is the derivative times the differential of x, right there. Now notice I have that. Let's rearrange it so we can see it a little better. So we have the e function being multiplied by negative 2x, and then there's the dx. Okay, so du is interchangeable with negative 2x dx. Here's a negative 2x dx. It's and du is interchangeable with that. Meanwhile, we said we were going to let u, the dummy variable, be negative x squared. So the dummy variable is interchangeable with that exponent. And let's not forget that we have this out here. So I have a negative 1/2 times the integration of e to the dummy variable, and then I just have du right there. Oh, well, if we're integrating e to the u with respect to u, we just slide the mother back in there rule. How about that? That was easy. But we don't want u talk, we want x talk. So we'll interchange again, because u and negative x squared are interchangeable, e to the negative x squared, and then don't forget your plus c bay b. There's the antiderivative using u substitution. Math made simple. Simpson math.